Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it. This is chapter 5.3, which is Riemann sums and definite integrals. Alright, so first let's talk about what a Riemann sum is. So, definition. Riemann sums. Let f be defined on some interval I, closed interval, IAB. If our interval I is partitioned into n intervals, or to say a subintervals, into n subintervals of with delta x, where delta x is b minus a over n, then the sum, so the summation from I equals 1 to n of f of c sub I delta x, where c sub I is just some point in the ith interval, alright? So some point in the ith interval. That is called the Riemann sum. Right, the Riemann sum of f over our interval I from A to B, right? So we already have seen something like that, right, in 5.2 with the problems that look like that. So we already know how to deal with that. But now, let's talk about the definite integral. So it turns out that if we start with the same conditions, right, f exists over this, right? So we're going to start with a Riemann sum. So we're going to have to make sure that f is defined on that closed interval, split up into n pieces and whatnot. So if the limit as n goes to infinity of a Riemann sum exists, that is, the limit as n goes to infinity of the summation from I equals 1 to n of f of c sub I delta x, if that limit actually goes to some value, L, where L is a real number, then f is said to be integrable on our interval I and is denoted as follows. So it is denoted, well, that limit, so the limit as n goes to infinity of that summation from I equals 1 to n of f of c sub I delta x, we can denote it as the integral from a to b of f of x dx. All right. So in here, that limit is called the definite integral. All right. So this is the definite integral. All right. So we call it a definite integral because it's actually defined over a specific interval, right? And here we're going from a to b. A is called the lower limit of integration. B is the upper limit of integration. All right, so now let's get a theorem here. Theorem. Continuity implies integrability. All right. So continuity implies integrability. So in other words, if f of x is continuous on the closed interval a b, then f is integrable over a b. Right? And what does that mean? So that is that the integral from a to b of f of x dx, remember this is a limit, right? That is, so this integral exists. So we're saying the limit actually exists. All right, so let's do an example of a definite integral. All right, and let's see what we're supposed to do here. So let's see. Example A. So let's say that we evaluate the integral from 0 to 2 of 3x squared dx. Right? Well, what am I going to do here? Well, the very first thing I need to do here is, well, let's see. What is the interval that we're working in? We're going from 0 to 2. So we're working from 0 to 2. So that's the interval that we need to work over. So what is it that we need? Remember that this integral is supposed to be the limit as n goes to infinity of a Riemann sum from I equals 1 to n of f of c sub I delta x. So delta x we already know to be b minus a over n. In this case, that's 2 minus 0 over n. So that's just 2 over n. And c sub I, recall that it was just some representative point on the interval, right? So if I talk about using the right endpoints, I can say it would be a plus I delta x, right? And then at this point we can say, well, what does this limit become now? It becomes the limit as n goes to infinity of the summation from I equals 1 to n of f of c sub I. Well, let's see. A was 0, so we have 0 plus I times delta x was 2 over n, so 2i over n. So we have f of 2i over n, and then delta x was just 2 over n. And here this 2 over n is not being affected by our index of summation here, right? So we have 2 over n times the summation from I equals 1 to n of plugging 2i over n into our function. Right in here, this is our function. So 2i over n into there, we have 3 times 2i over n squared. Actually, you know what? I'm going to put this back inside here. Nah, we'll leave it as that. And what am I going to do now? Now, in here, let's square this. So we have the limit as n goes to infinity of, we have the 2 over n times, well, let's see. This 3, this 2, and this n are not at all being affected by the index of summation. So let's get all those out. So 2 squared, that's 4. 4 times 3, 4 times 3 is 12. And then 4 times 3 times 2, so that's 12 times 2 is 24. So I'm going to have a 24 on the outside. We already had this n over here. Now for this n squared, well, that's n squared. But times this n over here, we end up with n cubed. And what do we still have? We still have the summation from I equals 1 to n of just I squared, right? And at that point, well, we know what that summation becomes. So we have the limit as n goes to infinity of 24 over n cubed times, well, actually, let's do n cubed times, this becomes n squared times n plus 1 squared over 4, right? No, sorry, that's the formula for I cubed. For the formula for I squared is n times n plus 1 times 2n plus 1. There we go. Way better. Over 6. Now, since n is going to infinity, we know from previous sections that this entire thing just goes to 1/3. So what we really have here is 24 times 1/3. 24 times 1/3 is 8. So there you go. That's what we had. That's what we get there. And what do we find here? Well, this Riemann sum, recall that it was, let's see what the function is. We had 3x squared, so that looks something like this. It's a parabola like that, right? And we were going from 0 to 2. And what we did there was we took a bunch of these rectangles, right? And we added them all up from here to here. Here's 0. All right, so that's what we got out of that. Now, I want to make an important note here. Definite integrals need not be positive. Definite integrals need not be positive. What do we mean there? Well, let's say that we had the following. Let's say we had a function that looks something like this, right? And we worked on the interval here from A to B. And in each piece here, we're going to be adding, well, all of these rectangles, right? These are the rectangles that we get out of this one. And then over here, we're going to get rectangles up to B, right? And here all the way from A. Now, what's my point here? The height of each of these is negative. So these are negative values. The height of each of these rectangles is positive. So these are positive values. But as you can imagine here, this piece right here, this is bigger in general than this piece. So this as a negative value is going to be much larger on the negative end than this is on the positive end. So overall, this Riemann sum will be negative. All right. So the thing about that is, well, we at one point sort of discussed formulas like these for the area under a curve. So while the Riemann sum can be negative, an area cannot. So let's explore that for a second. So theorem: the definite integral as the area of a region. So if f is continuous and non-negative on the closed interval from A to B, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals A and x equals B. Right, so that area is given by the following. The area is the definite integral from A to B of f of x dx. All right. So in here, what we're saying is, as long as we have a curve that throughout our entire interval from A to B, as long as that curve is always above our x-axis, right? So it's a positive function. Then this region can actually be considered the area, and it is given by the definite integral. So, all right. So let's find some areas. Sketch the region. Hold on. Let's phrase that better. Sketch the region corresponding to the definite integral. And use geometric formulas to find the area. So here we go. And this is example B. So let's say we had the definite integral from 2 to 8 of the line 3 dx. All right, so what does this look like? Well, in here we're going to say this is the line 3. That's just this line. And we're going from 2 to 8. In here, well, what shape is that? That's a rectangle, right? And remember, this was at the height of 3. So what does that tell us? Well, we have that this distance right there is 3, and this distance right there, we're starting at 2, going all the way up to 8. Subtract bigger minus the smallest gives us 6. So we have a rectangle here, so we can say that this is equal to 3 times 6. And 3 times 6 is 18. Cool. Next example. Let's say we had the definite integral from 1 to 4 of x plus 1 dx. All right. So let's see what that region looks like. So we have, all right, we have the line x plus 1. So we have this line x plus 1. And we're going from 1 to 4. And that's the area that we were trying to figure out. Now in here, what shape is this? Well, it's not a triangle. It's not quite a triangle, right? Because we're missing this piece over here. So what shape is this that we can actually find the area of it? Well, this is a trapezoid, all right? And for the trapezoid, the area is base 1 plus base 2 over 2 times the height, all right? So essentially, where this is base 1, and this is base 2, and this is the height. So, well, what are those values? Let's see. If I plug in 1 into my function here to figure out this height, right, this point right here, so 1 plus 1 is 2, so this is at the height of 2. So that means my base 1 is 2. If I plug in 4 into here to figure out what this height is, well, 4 plus 1 is 5. So that's at the height of 5. So base 2 is 5. And now our height here is the distance from 1 to 4. So 4 minus 1 is 3. And now we can figure out this area. So base 1 plus base 2, so 1 plus 5 over 2 times the height, which is 3. 1 plus 5 is 6. 6 times 3 is 18. 18 over 2 is 9. All right. Oh man, I messed that up, huh? My base 1 is not 1. That's awful. Should have told me. My base 1 is 2. So I have 2 plus 5. 2 plus 5 is 7. 7 times 3 is 21. 21 over 2. There we go. Way better. Way better when we do it without mistakes. Alright, cool. Good job, us. Let's keep going. D. Let's say that we have the integral from negative 3 to 3. The definite integral from negative 3 to 3 of the square root of 9 minus x squared dx. Well, what shape is that? All right, hopefully you already thought of the shape before I draw it for you, because I would like you to know what that function looks like overall. And that shape is a semicircle. All right, it's the top half of a circle. And this is going from negative 3 to 3. And the radius here is 9. Excuse me, the radius here is the square root of 9, which is 3. So it looks something like this. Alright? And the area of a semicircle. Well, a semicircle is half of a circle. And we know the area of a circle. The area of a circle is pi r squared. And what is the radius here? 3. So, well, hold on. This is for a circle. What about a semicircle? So, for a semicircle, would be, well, half of that, pi r squared over 2. And we've got the radius. Good. So what we can say here is that this is going to be pi times the radius, which is 3 squared over 2, giving us here 9 pi over 2. All right? Cool. Now, let's talk about some properties of integrals, of these definite integrals. If I take the integral, so hold on, so let's label it properties of integrals. And here's what we have. If I take the integral from a to a of f of x dx, that is 0. And that should make sense, right? Because we were using a whole bunch of these rectangles, right, to talk about the integral. And if I'm going from a to a, well, that width is just 0. So we're not really adding anything up there. The next thing that we're going to say here is the definite integral from a to b of f of x dx. Actually, that's not what I wanted to write. The definite integral from b to a of f of x dx is equal to the negative integral from a to b of f of x dx. So essentially, we can switch these bounds, right? If a is on top and b is on bottom, we can switch these bounds to put the b on top and the a on bottom by just multiplying by a negative 1 on the outside there, all right? All right, so what else? So this is the first one, this is the second one, this is the third one. For c being somewhere in the interval from a to b, right? So we're saying that c is somewhere between a and b, right? The definite integral from a to b of f of x dx is equal to the definite integral from a to c of f of x dx plus the definite integral from c to d of f of x dx. All right, and this should make sense, right? Because what are we saying here? So let's say, for example, we have the following. So I'm going to say that this region is going to be equal to the sum of these two regions, right? And in here we're going to say we have, let's say, something like this. This is A, this is B, and this is C. And perhaps I should not do that. I'll just copy this one. This is the integral from A to B, right? Over here, we're gonna look at what the integral from A to C is, and then over here from B to C. So what we're gonna say here is we've got this entire region is equal to the sum of this region plus this region, right? So that should make sense as to why this would be true, right? Next thing. So this will be the fourth. If I have the integral from a to b of a constant times f of x dx, this is going to be the constant times the integral from a to b of f of x dx. And integral from a to b of f of x plus or minus g of x dx would be the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. Alright, so essentially we can factor out a constant and we can distribute the integral symbol over addition and subtraction. Alright. What else? So that's 5, 6. If f of x is less than or equal to g of x for all x in a closed interval a b, right? Assuming, of course, that both f and g are integrable, then the integral from a to b of f of x dx would be less than the integral from a to b of g of x dx. All right, and this is assuming that they're integrable, so they have to be non-negative, right? In here, both f and g need to be non-negative functions over the entire interval. Now this should make sense, right? Because if I look at the graph here, right? Let's say here in blue we have f. Let's make that look differently. Let's say we have f, and then we have g. Let's do something like that. And we're going from A to B. Well, the blue area is just this, right? The area beneath the blue function. But the area beneath the yellow function will be the blue plus all of this, right? So in here, this is our function g, and in blue we have the function f. So essentially what we're saying is that inequalities are preserved over integration, all right? So let's use some of those properties to evaluate some integrals. So evaluate the following integrals. Evaluate the integrals using the following values. So let's say I had that the integral from 2 to 4 of x cubed dx is equal to 60. Let's say the integral from 2 to 4 of x is equal to 6, and the integral from 2 to 4 of just dx, or I can say 1 dx, but we know that's an invisible one. Let's say that's 2, right? And if I said, well, what is the integral from 4 to 2 of x dx, right? Well, in here, well, we know that we can switch these bounds by making the whole thing negative. So I can say the negative integral from 2 to 4 of x dx, which would mean that we get negative 6, right? Right, because this entire thing was 6. Let's say that we had the integral from 2 to 4 of 8x dx, right? And, well, what can we do here? Well, this can be rewritten as this constant here. I could put it on the outside, so I have 8 times the integral from 2 to 4 of x dx, and x dx was just 6, so we have here 8 times 6, so that's 48, right? Next, let's say we have the integral from 2 to 4 of x cubed minus 9 dx. All right, so let's see. We know first that we can split this up into two different things. So I have the integral from 2 to 4 of x cubed dx minus the integral from 2 to 4 of, of 9 dx, right? But that 9 there, I can pull it out here, right? Because it's just a constant. So I can just put the 9 out here and not in there. So at this point we say, well, what does that give us? We know the integral of x cubed. The integral of x cubed from 2 to 4. We said it was 60. So we have 60 minus 9 times the integral from 2 to 4 of just dx. That was 2. So 2 times 9 is 18. 60 minus 18 is 42. Right? 60 minus 20 would be 40. So 60 minus 18 would be 2 less than that. So 42. 2 more than that, I'm sorry. Taking away 2 less. Alright, whatever. H. The integral from 2 to 4 of, let's say that we have 1/2 x cubed minus 3x plus 2 dx. Well, what does that give us? Well, we can rewrite this as, I can pull out the 1/2, right? So 1/2 integral of x cubed dx minus, I can pull out the 3 integral, these are all from 2 to 4. From 2 to 4 of x dx minus, plus 2 times the integral of just dx, right? And at that point, what does that give me? That gives me 1/2 of 60 minus 3 times the integral of x was 6. So 3 times 6. And then plus 2 times 2, right? And what is that? Well, half of 60 is 30. Minus 3 times 6 is 18. 2 times 2 is 4. So 30 minus 18 is 12. 12 plus 4 is 16. Right? So there you go. That's all our definite integrals. And that's the end of 5.3. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.